Okay, for those of you who have joined us, we'll go ahead and get started. Welcome to the Next Limit Technologies and Rescale webinar. We're going to take you through how to set up and run an XFlow analysis on Rescale's cloud simulation platform. Before we get started, I'll go ahead and allow everyone to introduce themselves. My name is Ilea Gradle, and I am the Senior Account Executive at Rescale.
Hi, this is Mulyan Port at Rescale. I lead the applications engineering team here. We work with customers and with the ISVs.
And we also have Giuseppe from Next Limit Technologies. Giuseppe, I'll let you go ahead and introduce yourself. Giuseppe, looks like your microphone might be muted there real quick.
Oh, hi. Yeah, I was saying I'm Giuseppe Trapani. I'm an XFlow application engineer here at XFlow, and today I will be guiding you through setting up a test case in XFlow before running in Rescale.
And just a couple of housekeeping items. We will be recording and distributing this entire presentation later. And if you have any questions, please feel free to ask them in the questions section of the GoToWebinar panel. We'll be answering those at the end of the webinar today. But to just take you through the quick high-level overview, we'll be explaining more about what Rescale and the Next Limit Technology partnership is. And then Giuseppe will be going through a model setup of XFlow in XFlow, and then Moyanta will be showing how to run that model on Rescale's platform. So the platform that we have, we call it our ScaleX platform, and there's a couple of different versions to that. But essentially what it allows engineers and scientists to do is set up their workflows, set up their simulations using a very straightforward web-based environment. And Moyanta will show you in detail what this looks like. But essentially what you're able to do is access the infrastructure centers that are placed throughout the Americas, Europe, Asia, Australia, and leverage a large amount of high-performance computing power. That is coupled with the simulation software that we provide, and the Next Limit Technologies partnership allows us to provide XFlow in the cloud. And apart from just being able to set up and run those models, users can go ahead and monitor their simulations in real time, as well as perform post-processing. And what this web-based interface allows companies to do is easily control and manage engineering simulation resources. So this includes being able to track and monitor status of many different users throughout different teams, divisions, departments all around the world. And the ScaleX platforms can integrate with existing internal resources so that when internal systems become at capacity or there are no longer resources available and those lengthy queues start to form, they can transfer that simulation workload to the cloud and really leverage an on-demand system. Of course, one of the biggest concerns with using any external system or even internal resources is security. And so Rescale goes to great lengths to ensure that the platforms are secure and the the customer information is secure at every step of the way. And so we go through lengthy and in-depth processes every year to meet strict security, compliance, and regulation requirements. User data is encrypted at every step of the process, and that includes from the time it leaves the user's local machine. They upload those files to their Rescale account. They're encrypted in transit. They run on encrypted clusters, and then they sit in storage in an encrypted state as well. And so it's certainly something that Rescale is happy to have further conversations about, but we do go through to great lengths to make sure that the customer information and data is highly secure. In terms of a global base, I know we have quite a few global members of our audience today. Rescale is based in the United States, but our partners are globally distributed, and that includes software and infrastructure. And so you can just see here some of the centers that we have throughout the world. And what this allows us to provide is really an entirely, excuse me, customized environment where users can select high memory configurations, InfiniBand connection. We also have GPU instances available as well. And so it's a highly customized infrastructure environment that allows you to tailor each set of resources to the simulations that you're running. And then more about our Next Limit Technologies partnership. So Rescale and Next Limit Technologies have been partners now for coming up on a couple of years. And what it allows us to do is offer the XFlow simulation CFD software in the cloud. And Next Limit Technologies has allowed users to not only bring their existing licenses to run on Rescale, but to also use on-demand licenses. So when customers and clients experience that need for additional hardware and software, not only can they purchase the hardware on demand and only pay for the resources they need, but they can also purchase the XFlow software on demand as well. So it really allows for a true bursting environment in Rescale for running XFlow. Rescale's general platform is available globally, but this year we have also released a Europe region-specific platform. And so many of our European clients have data restrictions that allow or require them to keep all information within Europe or within European data centers. And that's exactly what the Rescale Europe region platform does. So it's the exact same environment. Users would be accessing XFlow and running their models in the exact same way they would on the general platform, but the hardware is limited and confined to within Europe. And so with the remote visualization capabilities that we also launched this year, users have the full end-to-end process of being able to set up the simulation workflow, to run the model, and to perform post-processing of XFlow entirely in the cloud without having to transfer all the information, constantly back and forth to your local machine. And Giuseppe and Moyanto will go ahead and demonstrate exactly what that looks like and how users can go ahead and run XFlow simulations on Rescale's platform. And with that, I'll go ahead and turn it over to Giuseppe to go through the XFlow model.
Okay, thank you, Ilya. Okay, as Ilya said earlier, well, I'm going to guide you through the setup of the model in XFlow. If at any point you don't see my screen, please do raise your hand or let the organizer know. First, I'm going to introduce a couple of slides which introduce, the motivation why we're developing XFlow, first of all, and then a little bit on the setup and the geometry itself. So let me jump straight through the motivation. So what's the motivation of developing XFlow? Well, I like these slides because it's what I call the CFD comfort zone. So yeah, I'm showing where basically Navier-Stokes, average Navier-Stokes code are comfortable, and we can see that relatively simple geometries, attached flow, and a transonic regime. The current Navier-Stokes solver are doing a good job. They are reliable, but all of these 3 points that I got in the main title are related to, well, first of all, the mesh generation limits the geometry that you can handle. So you want to really have simple geometries in there because you cannot mesh them otherwise. Attached flow is also a problem because when the fully detached flow, the simulation might have challenges in converging and it's not reliable the results they actually provides to the user. The resolution, well, and also the reliability of the results, it depends on the type of mesh that you use. So it's really highly dependent on the user knowledge and expertise. And also, well, transonic regime historical CFD has been developed for cruise conditions. So historically, CFD are really good in doing that performance analysis. But if you go beyond cruise, it becomes trickier to get accurate results. So what's the actual challenge right now in CFD? Well, is to go beyond this comfort zone of traditional CFDs and try to tackle problem in simulation that were unthinkable before. So, for example, can we have a reliable solution of unsteady aerodynamics for high turbulent flows, like stall or post-stall regimes? Or can we handle the actual CAD geometry directly into the CFD software without cleaning the geometry before doing the pre-processing? Can we have the same geometry using the wind tunnel data directly into our simulation environment? And finally, is it possible to analyze something really transient like low-speed buffets on set? So all these challenging questions of CFD currently, well, they are the challenge that I'm posing to the academia and to the industry. And what's the solution we're proposing? Well, XFlow. It's a lattice Boltzmann code, and basically it's a really extremely efficient way of doing large eddy simulation. So what we're doing is we are not using Navier-Stokes, average Navier-Stokes equations. We are solving the Boltzmann equation. It's a particle-based approach, so we don't need to have a traditional mesh process. So we skip completely the pre-processing. It's not depending on the solution is not dependent on the mesh anymore. It's not dependent on the expertise of the user in generating the mesh. And also it's a really high fidelity Lagrangian formulation. So it's inherently transient, it gives really accurate results, and it's a really efficient way of doing large eddy simulation. So those are just a few slides for the introduction of the motivation behind the development of XFlow. Now I want to really focus on the tutorial case for today. So I'm going to go through a few slides on the setup of the DLR F11 Wing Body configuration. And the first thing is to present the geometry. Well, this geometry has been used largely in the second AIAA CFD prediction of high lift. It's a workshop that was run during a few conferences, and there are many participants to the workshop. So if you want to have a better look, there is a website just at the bottom of the slide. You can check that out. But basically, it's a wind tunnel geometry developed by the German DLR Center, and is characteristic where it tries to mimic a realistic aircraft. The Reynolds number that we're going to analyze today is 15.1 million. There are two cases, a low Reynolds number and a high Reynolds number. That's what we're going to calculate today. And the Mach number is 0.172 because usually when you got high lift deployment, the Mach number is not really high. This configuration in particular is for takeoff case. So we got slat and flap deployed. And as you can see in the picture on the left side of the slide, we have the entire geometry in there. So that's the actual wind tunnel geometry. We have the flap track fairings, the slat tracks, and also all the tubing, which were used to actually carry the pressure from the slat pressure bundles back to the instruments measurements. Just an idea of the dimension of the geometry. We got a 3.07 length of the fuselage. In span is roughly 1.4 meter, and the height is just below 0.5 meters, so it's 0.32 meters. It's a wind tunnel model, so it's scaled, and we're gonna directly take the CAD input and put it in XFlow. How are we gonna set up the simulation XFlow? Well, you will see in a few seconds, but just to have an idea of the way we're gonna set up the simulation, well, we use in XFlow what we call the virtual wind tunnel. And it basically has a few setups already implemented into the code, into the graphical user interface, which helps in setting up the simulation, and you don't need to go to each boundary condition setup, for example. In this case, I'm actually going to change a few of the default dimensions. So the dimension is going to be 40 meters in X direction and 20 meters on the Y, which is the periodic condition, and 32 on the Z. As you can see, there is the plane in yellow. It's a really tiny one, but we use big domains because we don't want to have any influence of the boundary conditions on the solution. We're going to use an inlet velocity of 37.5 meters per second, and we're going to use a gauge pressure outlet of 0 Pascal. And finally, as I said earlier, we got periodicity boundary conditions on the side, on the Z-axis, and then a symmetry plane on the Y-axis. Just a table which summarizes the setup I'm going to do later on, but you're going to see that on the GUI anyway. So we said we got a Mach number of 0.175, which corresponds to a velocity of 37.5 meters per second. I'm going to adjust the kinetic viscosity and density in order to have the same Reynolds number of the wind tunnel results. And I'm going to use an angle of attack of 24 degrees. That's a really high angle of attack. And the simulation you're going to see is installed, but then you got highly developed turbulences in this type of flow solutions. Simulation time is going to be just 1.1 second because it's a transit simulation, but we want to run it for a long time in order to get to a converged solution, a steady state converged solution. And we're going to let the software decide for the time step automatically. So it takes into account the velocity condition and automatically defines the time step. Going to use a far field resolution. Of course, we're going to use a finer resolution on the aircraft surface so we can solve better the aircraft surface. And just going to put the reference area in the software. So when we got our coefficients back from the solution, they're going to be matching the experimental data. Now that's all. I don't want to bore you with any more presentations. So let's jump straight to XFlow. I think you can see my screen. So I'm going to just load and open XFlow. So that's the latest version of XFlow, XFlow 2015 and 96.01 is available from our website. And what I'm going to do is just create a project from scratch. So that's my environment in XFlow. And what I see here is my virtual wind tunnel. So I got my predetermined dimensions of the tunnel. And as you can see on the left side of the screen, and got different tabs, and in XFlow we're going to go through each of these tabs in order to get to the simulation tab where we actually run data and rescale. So the idea is really simple, keep the process really smooth and simple. Going from left to right, you're going to set up your simulation, and the last tab, of course, is post-processing. So once you get the data, you can do post-processing. So let me go to the setup. It's a 3D simulation. We can run 2D simulation, but in this case, we always run 3Ds. It's a single phase. XFlow has got different engines. We can have a multi-phase solution as well, or take into account free surface, but in this simulation, we're going to go for a single phase simulation. It's an external simulation, so we got the wind tunnel default, and I'm going to use automatic turbulence modeling. So let's go first for the reference area. As said, I'm going to use a custom value, which is going to be 0.12 roughly, so 0.41913. And that's the data or the value is going to be used in my simulation to calculate my coefficients, aerodynamic coefficients, so drag and lift coefficients. In this case, I'm going to input a reference velocity, which is going to be used by the software to automatically determine the time step to be used during the simulation. It's the inlet velocity I'm going to input in the wind tunnel, so it's 37.5 meters per second. And now I'm going to change the dimension of my wind tunnel. By default, it's a little bit small for this simulation, so I'm going to go and increase the dimension to 40 by 20 by 32. Okay, so now I've got a bigger wind tunnel, and I'm going to put my ground wall. I can use that as an actual ground wall, so if I got a velocity low, I can import in there. Or I can use it as a symmetry condition, so putting it as a free slip and zero velocity. That's going to be my symmetry condition on this side. And I'm going to input my velocity lows. Well, if I input 37.5 meters on the X direction, I'm basically going to have my simulation for zero angle of attack. Now I want to have an angle attack, so I'm going to introduce a cosinus and a sinus in the velocity lows in X and Z. In particular, there's going to be my inlet velocity per cosinus of 24 is our angle of attack. And since in XFlow we do use radians, I'm going to convert that, multiplying by pi and divided by 180. As you can see, I can actually input lows in XFlow. So I don't have to put just a fixed number. I can have a changing velocity, for example, with time. So I can just input the low in there. Just going to copy paste that in here. And this time I'm going to put a minus sign in front and a sinus, so that I'm going to have a flow which goes in this direction, so diagonally on X and minus Z. And this is going to input basically my velocity in the domain. By default, I'm going to have gauge pressure outlet and my n plus X. So now my setup of the wind tunnel is basically ready. So I'm going to change my materials to match the Reynolds number. By default, XFlow gives you the definition of the material is air, so you got reference density and operating temperature and dynamic viscosity, all congruent to air 15 degrees. So if I do change that to adjust to the boundary condition, to the wind tunnel conditions, in order to get the same exact same Reynolds number, that's going to be 8.62 minus 7. And I just change my materials. You can also put your own name on the materials, so you can change that to air, so you can just remember which material you're using. Now to the next tab, geometry. So far we have no geometry inside our XFlow, but we can import a few. So if I go to import geometry, I got in my machine in desktop, I got a few geometries which represent the geometry of the DLR F11, and I'm gonna just select all of them and import them. XFlow can import different files, different extension files, so I can import step and edges, which are parametric geometries. I can also import STL and NFB files, which are actually tessellated, so mesh files. As you can see, my geometry is no center, so in the wind tunnel, I actually want my symmetry plane to go through the half of the geometry to the symmetry plane of the geometry. So I'm just gonna go back to environment and move my wind tunnel to the position of 2, 10, and 0. What it's gonna do is actually moving the wind tunnel 10 meters on the Y, so I got a perfectly symmetric simulation. I could have done the other way around, I could have moved the geometry around, it's just a matter of preferences. Okay, so in the geometry tab, if I'm back here, now I got all my geometries listed in my project tree, and I got flap, fuselage, slat, wing, and slap track fairings, and tubes bundle. Those are really important because usually in other codes, those are not considered in the simulation. So I'm talking about slap track fairings and tube bundles. What I'm going to do, I'm going to show you quickly a nice feature of XFlow where we got independent geometries, but we can actually select each one of those and make it dependent on one of the geometry. In this case, if for example we have moving geometry within the simulation, which is a great feature in XFlow, we can have moving geometry which reference to the actual geometry they are a child of. So I got a father geometry and childs, which are going to be moving in reference to this reference system of the parent's geometry. What does that allows you to do? For example, if I want to rotate the entire sets of geometry, I don't have to go one by one and rotate them. I can just flip the parent one and all the child will actually flip at the same time. Okay, just a nice feature also of XFlow, we can set different materials for visualization. For this case, for example, I'm just going to set a metal look in the wing and select a different color. And so then you can use the same simulation software to do your video marketing promotion. And if you want to differentiate that, you can change the color. And I'm just going to do that so we can highlight especially those bits in here, which are what I said, the pressure bundles, which are a nightmare when you are doing traditional CFD because the meshing in these regions is really hard to get right. Okay, now we got geometry almost ready. What I'm going to do is just going through the boundary conditions. Those are our walls. So my geometry is actually an entire wall. And instead of using a wall model automatic, I'm going to use the non-equilibrium enhanced wall function, which does take into account separation due to pressure gradients. And in aeronautical, that's really important. In aeronautical applications, it's really important to take into account. So I'm going to just go and change all of those to the specific model. We do have a few other models, but well, the automatic one is basically the enhanced wall function. If you want to have any more information on that, please do send me an email or also check the user guide. Those are all defined in the user guide of XFlow, accessible via the help. So now that I got my geometry set up, the next tab is simulation settings. So I don't want to run the simulation for 20 seconds, it's far too long. So I'm going to set up simulation time on 0.1. And as I said earlier, the time step is actually going to be calculated automatically by XFlow using my reference velocity I specified earlier, which is 37.5, so it's my inlet velocity. And I'm going to select a different refinement algorithm. Well, you can use just one single lattice level, so one single resolution for the entire domain. That's highly inefficient. So what I'm going to do is select the near-static walls, so I can then refine nearby the geometry itself. I'm going to specify a resolve scale of 0.256. And as you can see, automatically, the resolve scale on the walls has been adapted. And there is a ratio of 2 between the two. And that's always the case in XFlow, because we use an octree structure, so we got a relationship between the fine and the coarse resolution. And in this specific simulation, I'm going to specify a resolution of 5 millimeters on each of the surface, but the fuselage usually is going to be a little bit coarser. It's going to be 2 centimeters. And I can also copy paste those. Okay, that's almost all I had to do concerning my lattice generation. Now I'm going to specify a transition length of 8 that indicates the number of rows I'm going to put in transiting from one lattice level to the next. And also I'm going to include a buffered zone length of 2. And that basically includes a region where there is a mix between the two lattice levels, and that helps the transition between the two. And that's basically it. I don't have to generate a mesh. I don't have to generate a surface mesh, a volume one. I don't have to specify if it's structure or unstructured. That's all done automatically by the software. The software executes a pre-process, generates the lattice structure, and then we run the simulation. One small step I'm going to do is to actually inputting the storage folder name. I usually like to give them sensible name, so it's High Lift Prediction Workshop 2, case 3 specific of that specific test case, and my angle of attack is 24 degrees. Last change, frames frequency. As I said earlier, the time step for the simulation is going to be evaluated automatically by the software, but we want to save our data at a different frequency, so we can specify that in here. And specifically, I'm going to use 200 Hertz, which gives me 20 frames. So you can see here that if I scroll my timeline, then I'm going to be able to see the solution of those different time steps. I can save my average results. So after the transition and the initial transition period, I want to have some averaging results. Of course, it's a transient software. So in order to get an average over period, I have to specify when I want to start my averaging. And usually I select at least half of the simulation. So I'm going to have a transition period and then transient period, and then I'm going to start averaging my result. And that's all the setup you need to do in XFlow. So if I go and save that in my desktop and call it that High Lift Prediction Workshop 2 case 3. Now I generated a setup file and a layout file, which I'm gonna go and see in this folder. So here I got all my geometries and plus 2 files, which are XFP, which is an XML file where the definition of the project is actually stored. So it's actually easy if you want to modify just one variable to modify the XML file. And then you can just load this file into Rescale and start the computation. So with that one, I'm going to stop the demo on XFlow side, and I'm going to go back to Ilya and show the Rescale side of the simulation.
Great, thank you, Giuseppe. So I'll go ahead and turn it over to Moyanto, who will go ahead and walk us through the Rescale portion.
Okay, thank you, Isaiah. Good morning or good afternoon, everyone. I'm going to walk you through the Rescale portion of this webinar. What you see here is the landing page of Rescale. It's what you see when you first log in to your Rescale account. It shows you a list of all the jobs that you've run or are currently running. You can filter this list by active jobs. We'll just show you currently running jobs, and saved jobs, which are just jobs that are saved but haven't been run yet. Another feature is on this page is you can organize your jobs, so you can create different directories to save your jobs in. So for example, I can create a folder called XFlow webinar, and then I can, for example, move my jobs to that folder like this. All right, so for this webinar, I will be showing you how to run the job that Giuseppe just showed you how to set up. I've got the input files on my computer, and I'm going to use those to run the job on Rescale. So to start setting up your job, you need to click the New Job button at the top of the page here, which will bring you to the job setup page. The first thing we want to do is give the job a name. So just going to give this job a very generic name here. And this is useful if you have to later reference a job. It would be easy to find. The second thing you want to do is to upload your input files. You have two options for your input files. You can either select input files that you've already uploaded previously. They will be stored under your cloud storage account. And if you want to do that, you have to click the Use Files from Cloud Storage option here at the top, which brings you to the file browser for your input files that you have already uploaded. But for this demo purpose, I will upload the files that Giuseppe just showed you how to create from my desktop. To do that, I'm going to click this Upload from this computer button, which will bring up your file system browser, and I'm already in the directory with all the input files, so I'm going to select all the files here and then start uploading them. So once you selected the files to upload, it will open up the upload status window, and it'll show you the progress of the upload for each file. The uploading process that we use is multi-threaded. So we try to saturate your bandwidth to optimize the transfer efficiency. We also encrypt your data client side before it gets uploaded to the Rescale data store. So once the files have been uploaded, you can see the files here in the selected input file section. You can, if you have to make slight changes to your input files, you can go ahead and edit your files here as well. But for this case, we don't need to do that. Since we have to reference the input file in our command, I'm going to copy the input file name here, so we can later paste that into our command. So the second step for setting up the job is to set up our software. So when we click on the software section of our job setup, we are presented with a list of all the software that is available on Rescale. we're going to use XFlow, so I'm going to go search for XFlow, and it'll filter the list of software according to your search term that you enter in the search box. I'm going to click the software here, and it'll bring me to the XFlow software setup page. On this page, we can do several things. The first thing you want to do is to select the version that you want to use. We want to use the latest version here that we've just installed, 2015 build 96. And then secondly, we want to specify the command that we want to use. So we want to run XFlow with this input file here. If you just want to run your job in a pure distributed mode, you don't have to change anything here. But since we want to specify one process per node, we want to specify the number of processes that we want to run. So in this case, we're going to run our job on 8 nodes. So I'm going to specify -n8 in front of our input file to specify that we're running on 8 nodes. The XFlow command here is a wrapper command that Rescale provides to encapsulate these 3 processes that are required to run XFlow. So it'll first run the generate binaries command to generate the binary files. It'll then run the generate domain command to generate your domain depending on the number of nodes you choose. And lastly, it'll run the flow solver. It'll pick the correct flow solver depending on what flow solver you chose in your case setup. So now that we've specified the command to run 8 nodes, the last thing we have to do is set up our licensing options. We provide 2 options for licensing. One is to provide your existing license, where you can point to your in-house license server. But we also, Next Limit Technologies and Rescale also offer a on-demand option. So that's what we're going to use today. It will show you the pricing schedule right here in the purchase license section. So once we've selected our license options, we are ready to select our hardware. So we'll go to the hardware settings tab here. And on the hardware settings tab, there are several things you can configure. The first thing you can configure is the core type. This basically gives you an option to specify a different hardware configuration on the core level. We have different configurations ranging from the value configuration marble to our Ivy Bridge nickel option, and we also have the latest Haswell Onyx option. We also provide several specialty core types. One special core type which may be useful for running XFlow simulations is the gold core type, which is a high memory core type configuration, especially if you decide to run on a lower number of cores. For example, this model requires at least 120 gigabytes of RAM. So if you were only to run on a single node, you would have to specify the gold core type because it would have 240 gigabytes of RAM per node. However, for this demo, we're going to run on 8 nodes. We're going to run on the nickel core type, which comes with 60 gigabytes per node and 16 cores per node. So let's go ahead and specify 8 nodes, which equals 128 cores. So we've selected 128 cores here, and then on the right-hand side, you can see the hardware summary. So we've selected 8 nodes with 60 gigabytes per node, and a total of 5.1 terabytes of storage. And so the last thing that I want to direct your attention to is the low priority option here. We provide a low priority option, which is a queued option. We use this qualitative indicator to tell you what the chances that or how soon your job is expected to run. So we can enable low priority because it's green here, or we can disable it if you want to just pay the full amount, price for a simulation. In general, the low priority pricing is about 60% of the on-demand pricing. In this case, we can just run on the on-demand pricing. So right now we've set up everything to run our job. We've uploaded input files, we set up our software, and we set up our hardware. So now we are ready to submit our job. And we can submit our job either on the review page or on the top right corner here. So we're going to go ahead and submit our job, which will bring us to the status page. So on the status page, you will see the status of your current job. Since we're running on demand, it's going to be in the queued state for a very short amount of time, usually less than a minute. So once it's accepted by our scheduler, then it'll go to validating input, which it is right now, and then it'll immediately move to starting cluster. It'll take about, depending on whether you choose low priority or not low priority, it'll take about anywhere between 2 to about 5 minutes to provision your hardware. So while we wait to provision our hardware, I'll talk about a few other features on this page. One feature is to you can share your job right here on this status page. This is useful if you want to share it with someone, with someone in your company who is also interested in the progress of the job or maybe even the results of the job. So you can share your job with anyone in your company. You can also share your job with Rescale support. So if I would like to have some help with setting up this job, I can select Rescale support here, and I can share my job with Rescale support. I can also leave a message to say like what I need help with, for example. The second feature here is you can clone the job setup, which gives you an exact clone of the setup. This is very useful if you're doing some maybe some bug fixing on your job or making small changes to your job. Since we're running kind of low on time, I'm just gonna move to an already running job to show you what an already running job looks like. So this is the status page on an already running job. You have this tailing section here in the middle of our status page. It will give you a little bit of a high-level overview of the status of your jobs. And then on the left-hand side, you can also filter the output files by using a search term. So I want to go really quickly through all those logs here. So the first log is the generate binaries log. So this might look familiar to you if you run XFlow in batch mode. The second one is to generate the main logs, and then the last one is the flow solver log. And it will show you all the standard out of your flow solver. Then lastly, there's also some other status you can look at. There's the cluster status. It'll show you an overview of the memory usage, your CPU usage, your network usage. So in general, overview of your hardware. And then lastly, I want to show you a finished job. So this is a job that Giuseppe ran earlier. This is the results page for a job. Similarly, you can see all the output files here and all the log files. You can download individual files. You can also download all the files as a single compressed archive. So that's basically your output files or your results page. And then lastly, I want to real quickly show you a new feature on Rescale called desktops. It's used for post-processing. You can get there by clicking the desktops button here at the top. To launch a new desktop, I can go to new desktop here at the top and just give it a name. And that will provision a desktop for you. I already have a desktop running here called XFlow Webinar. It'll give you a quick overview of what you can do with desktops. There's one section for node access. There's a section for attaching software to the desktop. We've provisioned the XFlow GUI on this desktop, and then a section for jobs that you want to post-process or pre-process on your desktops. So to access, to add another job to this desktop, what I would do is click the Add button here on the right, and then I would go here on the top and I would select Sync. To access the node, I would download either an RDP or VNC file, and then use that file to access the desktop. I've already got my remote desktop up here, and so this is the job that we were working on. We can move this around a little bit. So I'm not very familiar with XFlow GUI, but that's how you would access a desktop. Fortunately, this job doesn't have any output data, so let me go load a project that does have some output data. Just gonna load this job here. You can change these things. You can add, say, a cutting plane. And then change data here. And so this wraps up my portion of the webinar, and I think we'll
go ahead and turn it back over to Giuseppe to briefly show you what the post-processing looks like for the model that we actually ran on Rescale. Then if there's any time remaining, we'll get to questions.
Okay, perfect. Thank you. So what I'm going to show you now is just post-processing on the exact same setup we run in Rescale. In this case, we do have a few frames of the simulation, in particular on the time 0.09 second. So what I'm just going to do is a few cutting planes, which show the velocity in this case. And as you can see, it's smooth and average, because I'm actually plotting average results. So the instantaneities of the flow is actually filtered out and is averaged. And just another thing I'm going to show is a cutting plane on a different angle, in a different axis. In this case, it's total pressure, so we can see the total pressure losses due to the wake of the wing. In this case, you can just slide the cutting plane up and forward and select your visualization plane, and you can even specify a specific number, which is a dimensional with the dimension of the tunnel, or specify a specific arbitrary direction where you want to have your cutting planes. There are plenty of post-processing in XFlow. You can even build videos in it. So I'll just stop here, and so we give some time for questions to the audience. Okay. Thank you, Ilya.
Great. Thank you, Giuseppe. So we do have a couple of questions, and we'll go ahead and get started with those. So the first question is, why did you not set the time steps? And it says here, and I'm not sure exactly what portion it's referring to, but.
Yes, when I did my setup, I didn't set the time step, and I let the solver determine the time step which is needed to have a stable solution for the specified boundary conditions. So when I go to my simulation tab in XFlow, I can use this fixed automatic time step mode, or I can use a fixed custom. In the first case, what I just said to the software is, okay, consider you in the boundary conditions, and please give me a time step which gives me a stable solution for that. In the second one, fix custom, I'm actually specifying my time step. So in here, I can specify the one that I do think is going to give me a stable solution, and I can input any data I would like to. So there can be something like E-5. Okay, I hope that answered the question, but yeah. We can do both.
And then Moyanto, how does a user access hardware in Europe?
To access hardware in Europe, there's you can go to platform.rescale.eu. You need to sign up for an account on that platform, and that will sign you up to the platform.
Okay. We do have a couple of other questions that have come in, but just for the sake of ending around the top of the hour, what we'll do is when we send out the recording of the webinar and presentation today, we'll go ahead and Giuseppe and Moyanto can answer excuse me, the rest of the remaining questions in email. So I want to thank our presenters, Giuseppe and Moyanto, for their explanation of XFlow and the Rescale interface, and to our audience for joining us today. Thank you, everyone.
No, thank you, Ilya.